We created a one-hot encoding, a normalized count encoding, as well as a target encoding. Right? We went through three different types of encodings where you convert categorical values to numbers in different ways. And finally, I talked about the advantages of the so-called deep learning models, where you don't need to do much featureization or feature engineering. And that's one of the big advantages. So today we are going to uh, actually talk about what is perhaps the most important topic as far as this audience is concerned, which is how to evaluate AI models. Um, so the quantitative ways to evaluate AI models are often called metrics, and a brief overview of metrics. So first, when people train AI or develop an AI model, what is done is quantitative, certain numerical functions are optimized as part of the training process. And these are some metrics, right? So this is also what we call metrics. So AI model development happens through the optimization of certain metrics. And what do these metrics do? They measure the closeness between the predictions of the model and the actual ground truth of the labels. Right? You ideally you want the AI to be as close to predict things that are as close to ground truth as possible. So, so the way AI training works is there is a piece of code or an algorithm that tries to bring the predictions on the training data as close to the ground truth as possible. And this measure of closeness, when I say as close, this measure of closeness is called a metric. Okay. Um, Now, later, after the model has been developed and you start using it, then periodically we need to evaluate its performance. So the evaluation is also carried out using certain metrics that also measure the closeness between the predictions of the model and the actual ground truth. Now, there are some technical reasons for why the metrics that are used during AI model development may be different from metrics that are used for evaluating the model. This isn't always the case, but sometimes it is the case. So you don't need to worry much about the metrics that are used during development, but you will need to worry in the roles that you have. You will need to worry about metrics that are used for evaluating models, and we'll get to those in a minute. Now, there can be different types of metrics based on the different ways in which we measure closeness between predictions and ground truth. Right? So, one metric could be the average accuracy of the model, the sensitivity of the model, and we'll define all of these in the next few slides. So don't worry about the definitions at the moment, just worry about the names. So there's the sensitivity of the model, the specificity of the model, precision, recall, and so on. So all of these measures are metrics. Okay. Now, what is very important is that during the problem definition stage, it's very important that the key metrics that the AI model should aim to reach in a deployed setting must be identified. So at least the form of the metric, what is it? What is the metric? Do you want a model that will have high sensitivity? Do you want a model that will have high accuracy? This has to be identified early on during the problem definition stage. Because oftentimes in fact, not oftentimes, pretty much always, the AI model development relies on that definition. If you change the definition, the entire training process has to change. Okay, so it's very important that the key metrics that are important for deploying the AI model are identified early on during the problem definition stage. So I'll pause here for a minute. Are there questions? Is clear? Okay. Okay, so now to start a concrete discussion of metrics, we'll start with something called the confusion matrix. And in order to concretize things, let's suppose that we have an AI model that is a binary classification model. What is a binary classification model? it predicts whether data is in one of two classes. So an example for is an email spam classifier. Okay, so an email spam classifier is an AI model, and it tags an email as spam or not spam. This is what is happening in your Gmail in the backend. There is an AI model in the backend that looks at every incoming email into your inbox and decides whether or not to put it in the spam folder. Now, it often makes mistakes, but it learns from those mistakes. So if you have something that goes into the spam folder and then you move it to your inbox, then messages similar to that in the future you will see have less probability to also go into your spam folder. They will be rerouted. So this is an AI model that's actually working in the backend. And it's a binary classifier because it operates on emails and predicts whether the email is spam or not spam. Binary decision. Binary is two, so it takes a decision on whether the email is a spam email or a non-spam email. Right? Two classes. So let's say you have an email spam classifier that is evaluated on a bunch of emails, and just to make numbers concrete, say it's 921 emails. That's what these numbers in these boxes that you see, they total up to 921. Okay. So you can create this kind of table. There are different names for a table like this. In statistics, it's often called a contingency table, 2 by 2 contingency table. Uh, in the AI literature, it's often called a confusion matrix. So what does this table represent? So on the rows, we have the actual class, so whether the email is actually spam or non-spam. And the columns, we have the predicted class. And the entries in the various cells are the number of emails that fall into that category. Okay. So here we have 320 emails that are actually spam and are predicted by your AI model to be spam. Then you have 43 emails that are actually spam but predicted by your AI model to be non-spam. There are 20 emails that are actually non-spam but are predicted as spam, so they incorrectly went into your spam folder. Okay. And then there are 538 emails that are non-spam and predicted to be non-spam, correctly predicted to be non-spam. So the numbers in these two gray cells on the diagonal are the correct predictions, whereas the numbers in these two orange cells are false predictions of the AI. And as you can see, there are two types of false predictions. You can either have a false negative, and a false negative is uh, an email that's predicted to be um, non-spam, but is actually spam. So it's predicted negative, but is actually positive. Whereas a false positive is predicted positive, meaning it is spam, predicted to be spam, but it is actually non-spam. Is this clear what the contingency table, confusion matrix represents, the numbers in the confusion matrix? So if you add up these numbers, so let's say you add up the first row, 320 plus 43, which is a total of 363. That's the total number of actual spam emails, because that row corresponds to the actual uh, spam class. Similarly, the second row is the actual non-spam emails. The first column adds up to the predicted spam emails, 320 plus 20. And the second column adds up to the predicted non-spam emails. Any questions? Okay, good. So what we have here is a table that summarizes the accuracy of this binary classifier, namely the spam classifier. And as I said before, the binary classifier predicts that each data point will fall in one of two classes. We've described what is a confusion matrix. It's a matrix of data counts that captures all possible errors that such a classifier can have. Right? Um, And for a binary classifier, the errors are either false negative errors or false positive errors. Now, instead of, so this is because this classifier is a binary classifier, it's predicting only one of two classes. We call this a 2 by 2 confusion matrix. In general, if we had more than two classes, let's say 10 classes that the AI model was predicting, then we would have a 10 by 10 confusion matrix. So that's why we say if you're predicting one of k classes, we would have a k by k confusion matrix. Okay. Okay. Let's continue. So now let's look at various metrics that are defined with respect to this confusion matrix. And there's a little bit of maths here. Uh, you shouldn't uh, you shouldn't be scared of this. It's simple um, sort of school maths. You have your confusion matrix, and then you have these different accuracies. So first of all, there's the overall accuracy, which is just the ratio of correctly predicted emails to the total number of emails. Now, what are correctly predicted emails in this 2 by 2 matrix? It's the it's really the counts that are in the gray cells, right? The ones that are spam and are correctly predicted to be spam, and the ones that are non-spam and are correctly predicted to be non-spam. So this is true positives plus true negatives. And this is divided by the total number of emails. And the total number of emails is just the sum of all these four cells. So it's true positive plus false negative plus true negative plus false positive. So that's what I've written here. TP plus TN over TP plus TN plus FP plus FP. So TP plus TN is the total number of correct predictions, which is 320 plus 538. And that's divided by the total number of emails. And it turns out the accuracy of this classifier by this calculation is 93.2%. Okay. We can also define the sensitivity, and the other word for sensitivity is recall. So the sensitivity of this classifier is it's if you take the total number of um, actual positives, which is actual spam, right, which is 320 plus 43. What are the proportion of actual positives that are correctly predicted by the classifier? That is sensitivity. Okay. It's also called recall because it tells you how many of the true positives, how many of the actual positives are recalled correctly by your classifier. That's why it's also called recall. So in order to compute sensitivity, what you do is you take 320 plus 43 in the denominator. So that's true positive plus false negative, and that's 363. And you divide 320 by 363. So it's a number of, um, it's a proportion of positives that are correctly identified by the classifier. Is this clear? So this turns out to be 88.2%. Similarly, you can define specificity, which is similar to sensitivity, except that it works on the negatives. So you take the total number of negatives, and of those, how many of them are correctly predicted? The total number of negatives are 20 plus 538, actual negatives. And the ones that are correctly predicted are just 538. So we divide 538 by 558, and that's 96.4%. Okay. So again, accuracy is total number of correct predictions, total proportion of correct predictions. Sensitivity is proportion of positives that are correctly identified. Specificity is proportion of negatives that are correctly identified. Okay. Then you have precision, or this is also called positive predictive value, PPV. The precision is slightly different from sensitivity in the sense that what it measures is of those that are predicted to be positive by a classifier, how many are actually positive. So precision works along a column, whereas sensitivity works along a row. So, so how many are predicted to be positive or predicted to be spam by the classifier? Anyone? Without peeking at the calculation. Any thoughts? Any guesses? So just based on this uh, table, how many of these are predicted to be? How many emails are predicted to be spam by the classifier?
340.
340, right? 320 plus 20, because that's the total number predicted spam. And out of those, the number that are actually spam are 320, right? So I'm taking 320 dividing by 340 to get the precision, which is 94.1%. And then if you do the same thing with the negatives, how many negative, how many of the predicted negatives are actually negative? Um, you get the negative predictive value. That doesn't have another term associated with it. It's just called NPV. So that is, you add up the total number of predicted negatives, which is 538 plus 43, and that's 581 here in the denominator. And so you have 538 divided by 581, which is 92.6%. So now you can see that each of these metrics actually exposes, um, and we'll see this in the subsequent slides as well. Each of these metrics exposes a different characteristic of your classifier. You can see all these metrics take different values, but they all measure in some sense an accuracy in different ways. If your classifier was perfect, meaning it didn't make any errors at all. So if this number was 0, false negative was 0, and false positive was 0, then all of these metrics would be 100%. Excuse me. But now, depending on how many are false negatives, how many are false positives, what is the ratio to the true positives and the true negatives, depending on that distribution, you will get different numbers for accuracy, sensitivity, specificity, precision, and NPV. And you can see all these numbers are different. Now, in this case, actually, all the numbers are fairly high. So we can safely say that this is a good classifier, maybe. But you can often run into situations where one number is high, another number is low, and that's where you need to really understand which is the metric that is important to your problem and important to identify this upfront. Okay. So one thing you should note is you really just need to, I mean, accuracy is what it is. It's just the proportion of correct predictions. But you just really need to know what is sensitivity and precision, because once you interchange the definition of positive and negative, you get the other two metrics. So if you change positive to negative, you go from sensitivity to specificity. You change positive to negative, you go from precision to NPV. Okay. Now there's another quantity of interest that you can derive from this table. You can calculate from this table, and that's called the prevalence, which is not really a metric, but it's often a very useful characteristic of your data set. Okay. So in this case, prevalence is really spam prevalence, and that is simply the total number of spam emails divided by the total number of emails, meaning the proportion of emails that are actually spam. Now, the total number of emails is 921. How did I find the total number of spam emails from this table?
The first row, right? 320 plus
First one, right? It's the actual spam emails, 320 plus 43. Yes. So that gives me 363. 63 divided by 921. That tells me the prevalence of spam in this data set is 39.4%. And this is very useful to know for your data set typically. Okay, if this is clear, then I'm going to move on.
Alpan, we come across this term called F1 or
Yeah,
F1 value.
yeah. Don't worry about that right now. It's
Okay.
not that important.
Okay.
I mean, it's typically used in uh, internally by ML scientists. It's not, in most cases, it's not relevant for evaluating AI models in the real world in most cases.
Okay.
So I didn't want to get into too many different metrics. But yeah, there are other measures of accuracy as well.
Mhm. Okay.
Okay, so let's just do a little bit of a recap. Um, First, what is a classifier? A classifier is an AI model used for classifying data into one of many categories, right? Or classes. A binary classifier is one that predicts one of two classes. Right? Multi-class classifier is a classifier that predicts one of many classes, more than two. Okay. Accuracy of a classifier is proportion of correct predictions. Sensitivity or recall is the proportion of actual positives that are caught by the model. So let me again iterate that here what in the context of the spam example, we decided to call spam emails as positives and non-spam emails as negatives. And it's just terminology. You can switch the two. It just depends on what is your category of interest, and that will dictate what you call positive versus negative. Specificity is the proportion of actual negatives that are caught by the model. Right? So if you interchange positive and negative, you go from sensitivity to specificity. Precision or PPV, positive predictive value, is the proportion of predicted positives that are actually positive. And NPV is the proportion of predicted negatives that are actually negative. Sorry, is there a question? Yes, Mihir. So we'll discuss that in a minute. Real world examples. Yeah. Okay. Um, so just like we had accuracy metrics, we also have error metrics, which are sort of the complements of the accuracy metrics in a sense. So it's the same confusion matrix, the same numbers, etc. But instead of accuracy metrics, we have error metrics. So we have the false positive rate, which is one minus specificity. So the false positive rate is the proportion of um, uh, the proportion of negatives that are false positives. So it's an error rate. Similarly, the false negative rate is the proportion of actual positives that are predicted to be negative. Again, an error rate. And so false positive rate is 1 minus specificity, false negative rate is 1 minus sensitivity, and then there's something called the false discovery rate, which is 1 minus precision. And you can calculate all of these uh, for the same data set. Okay. Okay, there are some questions. Can you say them aloud?
So the question was from me, Alpan, but nothing like urgent as of now. If later on, if
Okay,
we have time, we can go through the LFU slides for these terms. I thought that would be useful.
sure. I can ask Mihir if you have access to them, then at some point Mihir could show them. Another question.
No, it's not a question. I mean, just to everyone can remember like this.
Oh, I see. 1 minus sensitivity, you have an N, is
And,
false negative rate, and 1 minus specificity, you have a P, so it's
yes.
false positive. So it's a good way to remember. Yes. Doesn't work for false discovery rate, but that's okay. Okay. So I wanted to get into a discussion of class prevalence and what that has to do with all this. So we've talked about class prevalence, which is really the proportion of data belonging to one of the two classes, right, in a binary classification situation. So this is not, class prevalence is not an attribute of the AI model. It has nothing to do with the AI model. It's just the data. It's just what the data is. It's an attribute of the data distribution. But what happens is if your prevalence is highly skewed, so by skewed, I mean that one class is much more prevalent than the other. So in the spam example, for example, um, let's say your spam emails are just 1% of total emails, right? So spam emails are very few, whereas most non-spam emails are 99% of all emails. Then that's a highly skewed data distribution. So what happens is if prevalence is highly skewed, some metrics can look really good, regardless of how good the model actually is, right? So for example, let's suppose spam email, as I mentioned, is just 1% of all your emails instead of the value it took in the example that I showed you, which was 39.4%. So your prevalence is 1%. And suppose my AI model predicts all emails, regardless of what they are, to be non-spam. What would be the accuracy of this model? Can someone
Nine.
someone let me know?
99.
So what percent of emails will be correctly predicted? 99%. Yes. So it will be 99%, right? So if you just look at the accuracy, you would imagine that this is a really good model, right? But is it a really good model?
I think recall would be more important here.
Recall actually is what is your yeah. So what is your spam recall for this model? The recall is actually 0 because it's predicting all emails to be non-spam.
Yeah, yeah.
Right. So you can see that you have a situation where one metric, one accuracy metric, namely the overall accuracy, is really high, 99%, whereas another accuracy metric, namely the recall, is really low. Right. In fact, it's 0. Right? So the metric you track is very, very important. Okay? Now, there are some metrics that intrinsically measure the model quality independent of what the prevalence is. Right? And there are other metrics that take prevalence into account, and they're both important in different contexts. So the metrics that don't depend on prevalence are sensitivity or recall, the specificity, the false positive rate and false negative rate. Those are the error metrics. Whereas the metrics that do depend on prevalence are accuracy, precision, false discovery rate of all the metrics we've discussed. So for example, if we go back to the previous one, and let's say I increase my prevalence, suppose the prevalence of spam email was 20% instead of 1%. But the classifier did exactly the same thing. That means that it predicts all emails to be non-spam. The recall doesn't change. Right? The sensitivity doesn't change. It's still 0. The sensitivity actually doesn't depend on prevalence, right? But the accuracy changes. Accuracy is now 80%, not 99 anymore. Is this making sense?
Why false positive and false negative rate won't be affected by prevalence when precision is affected?
False positive rate is 1 minus specificity. False negative rate is 1 minus sensitivity. Sensitivity and specificity are not affected by prevalence.
Oh,
Therefore,
right. Positive and negative
FT.
predictive values are affected. Right.
Yes, so FDR is affected. Yes. Yes.
Okay.
Yes. So let's say you have a concrete example, right? Suppose you have a diagnostic test for a type of cancer, and the cancer itself has a prevalence of 0.1% in the population, which is actually a high prevalence, but just for the sake of this example, the test has 100% sensitivity and 99% specificity. So these numbers look really good, right? What is the precision of this test? So let's take some concrete numbers. Let's walk through this example in our heads. Okay, so let's take some concrete numbers. So let's say you are evaluating this test on a population of 1,000 people. Why did I choose 1,000? Because of this 0.1% prevalence. If I have 1,000 people, there will be one cancer case in 1,000 people, right? 1 in 1,000 is 0.1%. So let's say you're evaluating on a population of 1,000 people. We know that actually 1 out of those 1,000 people has cancer because that's the prevalence of cancer in the population. Now, this test has 100% sensitivity. That means the one cancer case will be correctly identified, right? Remember, sensitivity is the proportion of actual cancer cases that will be detected correctly. And since that's 100%, the one cancer case will be correctly identified. The specificity, however, is 99%. Now, what is specificity? The proportion of negatives that are correctly identified. Now, how many negatives are there in this population? How many people don't have cancer?
999.
No.
One has cancer, so the remaining does not have cancer.
Yes. The number of people who don't have cancer, you're right, is 999. Correct. And on that 999, how many of those will be identified correctly?
99% of them.
99% of them. So that is 999 minus, so 1% of 999 is 9.99. Say we can round it to 10. So 999 minus 10, which is 989, right? So out of the 999 who don't have cancer, 989 will be correctly detected as not having cancer. The remaining 10 will be predicted by the test to have cancer. Correct? Do
Right.
people understand the argument? So, so the one person who has cancer is predicted to have cancer, plus 10 more people who don't have cancer are also predicted to have cancer by this test. So what is the precision of this test? What is precision? Precision is
15%.
among those who are predicted to have cancer, how many actually have cancer? Now, 11 people are predicted to have cancer, and only one of them has cancer. It's less than 10%, 9 point something. So this test has very good metrics as far as sensitivity and specificity are concerned, but its precision is really low, like just 9 point something percent precision. So people understand this argument so far. Please stop me. Please ask me questions if you don't. It is important to get these things. I mean, these are metrics we'll all be working with on a regular basis, and already working with, in fact.
I think our LFE model has more or less similar precision, 8 to 9% at certain level of.
Correct. Absolutely correct. Yes. So now so we found the precision. The next question is it a good diagnostic test? And what would be the answer? Is this a good way to diagnose cancer?
If it's a screening test, probably okay. But
No, the question is it a good diagnostic test?
definitely not for confirmation.
Yeah, it's not a good diagnostic test. It's not a good it's not a good way to have a diagnosis, because majority of the people it is predicting to have cancer actually don't have cancer. So you can't use this for a diagnosis. So sensitivity, specificity doesn't tell you everything. You really have to look at the prevalence in order to know if this is a good diagnostic test or not. On the other hand, this is a pretty good screening test. Why is it a good screening? What is the difference between a screening and a diagnostic? A screening test is a test that you initially take to rule out the disease, right? So if the test tells you because it has 100% sensitivity, if the test tells you are negative, that means you definitely don't have cancer. On the other hand, if the test tells you you're positive, you have to go for further testing, which would be a diagnostic test. So it's very good for doing that, but it's not good as a diagnostic test by itself. So based on these numbers and this analysis, you should be able to come to conclusions like this, right? This actually has nothing to do with AI. These are things that you do anyway to judge, diagnostic tests, screening tests, and so on in a variety of public health situations. This has nothing to do with AI. Questions? Okay. So let's look at this a little more closely. So first, I think we've already addressed this to some extent. So first, I want to make the case that just using your accuracy metric can hide information. And let's make this more sort of clear. So here I have two different confusion matrices, right? Again, let's not confuse matrix from metrics. They're two different, I think, unfortunate terminology. So here I have some AI classifier being evaluated on a population of 505 people. Okay, that is this n equals 505. Okay, in both cases, it's being there are two different AI models actually, both being evaluated on a population of 505, both trying to do the same thing. Okay, and we have confusion matrices for each of these classifiers. So actual class, positive, negative, predicted class, positive, negative. So you have 500 individuals who are actually positive and predicted to be positive. 0 individuals who are actually positive and predicted to be negative. Okay. 5 individuals who are actually negative but predicted to be positive. So that's an error. And then again, 0 individuals who are actually negative, predicted negative. So the blue numbers are the good numbers, and the black numbers are errors. Now, if you look at the other classifier, it's doing something a little bit different. Out of 505, 450 are both actually positive and predicted positive. 4 are actually negative and predicted negative. 50 are actually positive but predicted negative, and 1 is actually negative but predicted positive. So the 50 and 1 are again errors. So in the first case, what is the accuracy of this classifier? 99%. This is very similar to the previous example on spam that we had. It's got 99% accuracy. But what is it actually doing? It's predicting everything to be positive. That's all it is doing. No matter what individual who comes, if you think of this as some kind of test for a disease, predicting everybody to be positive. Right? And so it's not very useful. And it has 100% sensitivity. So you have 100% recall on the positives, but 0 specificity. Right? None of the negatives are being caught by the test, actual negatives. On the other hand, the second test has lower accuracy. There's only 90% accuracy because you can find accuracy by adding the two blue numbers and dividing by the total. So 454 divided by 505, 90, roughly 90% accuracy. But it's actually a much more useful test because it doesn't just predict everybody to be positive. It's doing some discrimination, right? And so it has high sensitivity and high specificity, even though the accuracy is lower than the previous test. So often we have a tendency, and I've seen this in our team itself, to just quote the accuracy of some AI model and imagine that the accuracy actually encapsulates everything. It doesn't. And this is an example. Yeah. Here's another example. So this is a sort of converse example where sensitivity and specificity don't encapsulate everything. And we've seen a similar example before. So now we have two models acting on two different populations of different sizes. So the first model is being evaluated on a population of 950 people. Second model on a population of 1045 people. And these are the confusion matrices. So what's happening if you compute the accuracy in both cases? If you compute sensitivity and specificity for both models, they're exactly the same. So here the sensitivity is 80% because 400 divided by 500 is 80. Here it's 80% because 800 divided by 1000 is 80. Specificity is 80% because 200 divided by 450. Did I do this correctly? Is 200 divided by 450. I may have made a mistake here. Sorry, it's not 80%.
But it is same in both the examples.
It's same. Yeah. Sorry, I just copy pasted. Can someone do this calculation and tell me what it should be? 200 divided by 450. And that's the same as 20 divided by 45. It's like 40 something percent.
44% roughly.
44%. Yeah. So specificity in both, sorry for the typo here, specificity in both is 44%. So you see, as far as sensitivity and specificity go, both of these classifiers are equally good. But if you look at the accuracy, so remember sensitivity and specificity do not depend on prevalence. Whereas accuracy and precision do depend on prevalence. You can see the prevalence of the positive class is very different in both cases. So here, what is the prevalence of the positive class? You don't have to actually calculate, but can somebody tell me numerator and denominator? Somebody other than Malay. Malay has a public background.
Hello.
Hello.
Yeah. Wouldn't it be 250 divided by 450 specificity?
Sorry, 250. Yeah, you're right. 250 divided by 450. You're right. Not 200. So it's 50 something percent.
Yeah.
But it's the same. It's the same. You're right. Absolutely. But it's the same in both cases. Right? Okay. So, yeah, what is the prevalence in the first case? Prevalence of the positive class? What's numerator and denominator?
$400 divided by 950.
Who is this? Who is
Sanchik.
this? Sanchika. No, what is the prevalence in the first case? It's not 400 divided by 950. Remember, prevalence is just the proportion of examples in the positive class.
Is it 400 divided by 950?
No. Yes. Just speak up.
So 500 divided
500 divided by 950 because the actual number of positive examples is 400 plus 100. Right? So 500 divided by 950 is a little over 50%. What about here? What is the prevalence of the positive class?
A 1,000 divided by 1,045.
1000 divided by 1045, and that's much higher, right? So that's over 95%. Whereas here it's just over 50%. So the prevalences are very different in these two populations, right? And that affects the accuracy and precision metrics because they depend on prevalence. So here the accuracy of this classifier is 68%. Here the accuracy is 79%, even though sensitivity specificity are the same for both. Precision here is 67%, whereas this has a much higher precision of 98%. Yeah, and that's because it's predicting very few negatives. So, okay, there's one more point I want to make here. So typically what you do in cases like this is when you compute the precision, you can directly compare it to the prevalence. So here the prevalence is 90 odd percent, precision is 98%, right? And so you're getting a little bit of a lift above the prevalence. Similarly here, precision is 67%, but prevalence is just some 50 odd percent. And again, you're getting some lift above precision. So prevalence, if you were to just classify people randomly, then for that random classifier, the precision would be the prevalence. Okay? And we will come back to this concept a little bit later. Okay, so so now that you understand what a classification model does, at least for a binary classification model or a binary classifier, you understand that it predicts each individual or each data point to be in one of two classes. So how does it operate? So so this is how we've discussed a classification model so far. Now, if you have an AI classification model, the way it typically works is it doesn't directly predict your instance to be in a positive class or negative class. What it instead predicts is a score between 0 and 1, which says, okay, if you have a score of 0.8, that means you're more likely to be in the positive class than the negative class. On the other hand, if you have a score of 0.3, you're more likely to be in the negative class than the positive class. So in a sense, it predicts a for the sake of simplicity, I'll call it confidence. It predicts a confidence of being in one of those two classes. Okay? So how do you convert it to an actual classification model? Well, here's what you do. So you have your features, they feed into the model. The model outputs a score. So a score, again, think of a score as being a number between 0 and 1. Okay? Then the AI team, in collaboration with the program team, decide on a threshold for this score. So they say, well, if the score is above 0.6, let's say my threshold is 0.6. So we say if the score is above 0.6, let's call it a positive prediction. If it's below 0.6, let's call it a negative prediction. So now you predicted, so my 1 is a positive prediction, 0 is a negative prediction. If my score is bigger than the threshold, and I predict it to be in one class. If it's below the threshold, I predict it to be in a different class. So now you've converted an AI model into a classifier for which you can compute, you can calculate a confusion matrix. Okay, because it's predicting for each data point that whether it's in one class or the other class after you apply the threshold. So this is what I'm saying here. What a classifier does is it typically outputs a score between 0 and 1 that loosely corresponds to the predicted probability of a class. It doesn't directly predict the class label. So what we need to do is to choose a threshold, and this threshold is called this threshold or cutoff. It's also often called a cutoff. Is called the operating point of the model. Okay, and so we say, whenever the score is above the cutoff or threshold, a certain label is predicted. So, for example, in our LFU model, if the predicted LFU score, let's say our cutoff is 0.71. So if the score is greater than 0.71, we will predict the patient will go LFU. If it's less than 0.71, we will predict the patient will not go LFU. And so this operating point is 0.71. How did we choose 0.71? That's something we'll come to. So the main message I want to convey with this slide is that even after you build an AI model, there is one very important choice that remains to be done before it is converted to a classifier, which is choosing the operating point of the model. And that cannot be done algorithmically. That is done on the basis of what are the metric values that are desired. What is the important metric for the problem at hand? And that's what we'll come to. So often what happens is the operating point is not defined based on a risk score cutoff, but on the value of a metric. So for example, if you say that you want a sensitivity of 90% at 70% specificity, that often defines an operating point for you, because there's only one value of the threshold that will give you, if at all, that will give you the sensitivity at this specificity. Ideally, the operating point should be defined by program folks, domain experts, because the operating point will decide both the impact and the accuracy of the resulting AI model. And once you decide the operating point, then you can compute your whole confusion matrix, compute sensitivity, specificity, precision, recall, etc. But that can only be done after the operating point is decided. So it's important to realize that if you change the operating point, if you change this threshold, if you change it from 0.7 to 0.4, that will change all your metrics, the values of all your metrics. And if you change it continuously, these values will also change continuously. And we know that some metrics, actually we haven't come to this yet, but there are some metrics that are independent even of operating point. And they're very useful for optimizing the model in development, because when the AI model is in development, you haven't yet chosen your operating point. So you want to work with metrics that don't depend on operating point. So often that's the case. So there are metrics that are useful for development, but not so useful in practical settings. So some examples. And in order to get to those examples, I know that some of you are already familiar with this, but I also know that many of you are not. So I'm going to discuss this this XY space called ROC space. This is a good way to visualize the performance of your classifier, and that is in ROC space. So what is ROC space? It's a space in which you can visualize the accuracy or performance of your classifier independent of what the prevalence is. And what do the X and Y axis mean? So the X-axis is false positive rate, which is 1 minus specificity. Y-axis is true positive rate, which is sensitivity. So you're plotting sensitivity versus 1 minus specificity. Now, if you have a good classifier with a good classifier will typically have high sensitivity and high specificity, right? So if the specificity is high, that means 1 minus specificity is low. So if you have a point somewhere in this region, you have high sensitivity, but low value of 1 minus specificity, which means high specificity. So this sort of top left-hand region of the space corresponds roughly to good classification performance. A straight line at 45 degrees in this space, which is sensitivity equals 1 minus specificity, that's a random classifier. That's actually not very good at all. It's just like doing a coin toss and deciding whether you want to put that data point in one class versus another. Okay? And so a bad classifier is something that is close to this line. Okay. And so basically close to a random, close to random performance. On the other hand, what about classifier? Can someone sort of guess what's happening here? So here you have this blue classifier has low sensitivity and low specificity, very low specificity. So what would you call this? I've actually already spelled out uh, what the problem is here. So ordinarily you would call it a really bad classifier because it has low sensitivity and low specificity. But the thing is that if both are low, then all you have to do is take exactly the opposite decision of what the classifier says. So in other words, if you predict, if the classifier predicts that uh, something belongs in class A and your decision is to put it in class B, whereas if the classifier predicts it belongs to class B, your decision is to put it in class A. So you just invert the prediction of the classifier, then you get a very good classifier. So typically this region is not a realistic situation because you can just invert the predictions and get a very good classifier. So this bottom right corner scenario is typically unrealistic in practice. So usually we say that if something is in the top left corner, that's a good classifier. On the other hand, if something is close to this 45-degree line, it's not a good classifier. Okay. Am I going too fast? Or are you guys okay? Okay, I'm going to assume everybody's okay since people are silent. People are either silent or sleeping in the afternoon. Maybe that's not a good time. Okay, so now that we know what is ROC space, we're going to go ahead and discuss something slightly more complex, and I'd like to spend sufficient time on this because I want everybody to understand this. We're going to discuss something called the ROC curve. So I'm going to go back to, so let's say we have a data set, right? So I have patients and I have an AI model that's predicting the risk score of some disease. Okay. So this column here is just the ID of the patient. It can be anything. Okay? And then I have these risk scores, and let's say your data set is ordered in such a way that these risk scores are in decreasing order. So I put the patient with the highest risk score on top, second highest risk score after that. It's just the way I order people in this data set. Okay. So this guy A has a risk score of 0.99 and so on. Okay? The risk scores keep decreasing. And then there is this column corresponds to the actual ground truth for that patient, meaning does the patient have the disease or not? 1 means the patient has the disease, 0 means the patient doesn't have the disease. Okay. Now, how do I choose an operating point? Remember, the AI is outputting a score. It's not outputting, this is the output of the AI. The second column is the output of the AI. It's not outputting 0 or 1. It's just outputting a score. In order to convert this to 0, 1, I have to set a cutoff or a threshold, right, which is the operating point. So suppose my operating point is the blue line here. What does that mean? That means every patient above the blue line is classified as having the disease by the AI. And every patient below the blue line is classified as not having the disease by the AI. Right, so all of these are 1, these 3 are 1, that's the predicted label, and all of these are 0, that's the predicted label. Is that clear? Yes, no, maybe?
Yes.
Okay, good. So now don't forget about the other, forget about the purple and orange lines for now. Let's just focus on the blue, okay? So if I assume that my operating point is the blue line, then and I call this operating point 1, right? The cutoff for the operating point is 0.9, meaning any score above 0.9 is predicted to be having the disease or positive, whereas any score below 0.9 is predicted to be negative. That's how we are setting the cutoff. So what is the sensitivity of this kind of classifier? How will we calculate this? So I've shown you the calculations here, but we should be able to do this in our head. So what is sensitivity? Sensitivity is the proportion of actual positives that are correctly detected by the AI. And what are the actual positives? They are the total number of ones here. 1, 2, 3, 4, 5, 6. There are 6 ones in this column. So there are 6 actual positives. Of these 6 positives, how many are correctly detected by the AI operating at this threshold or this cutoff? Well, the AI is going to predict everything above this to be 1, right? So only 2 of them will be correctly detected by the AI, right? So the sensitivity is 2/6, which is 0.33, 33%. What is the specificity? Well, look at all the negatives. So how many negatives do I have? Just calculate, just count the number of zeros. 1, 2, 3, 4, 5, 6, 7. There's 7 zeros. Of these 7 zeros, how many are correctly detected by the AI? Well, according to the AI operating at this blue threshold, everybody below the blue line is predicted to be 0, right? So the only true 0 that is missed out is this one above the blue line. So of the 7 zeros, the AI has correctly detected 6 of them. So the specificity is 6/7, which is 86%. And from that, you can calculate 1 minus specificity, which is 0.14. So I can use these values, sensitivity of 0.33, 1 minus specificity of 0.14, to plot a point in this on this graph, right? And that's my blue point. So my 1 minus specificity is 0.14, my sensitivity is 0.33, and I plotted this blue point. Yeah, I can do the same thing with choosing a different operating point. So there's this purple operating point which corresponds to a cutoff of 0.59, meaning any patient who gets a score greater than 0.59 is classified as positive by the AI. Any patient below is classified as negative by the AI. And again, you'd repeat the same calculations. Let's go through it once more. I won't do it the third time. But you have a total number of 6 positive patients. There are 6 ones in this column, just like earlier. Of those, 5 are caught by the AI correctly. 1, 2, 3, 4, 5, because they are above this purple line. There's only one that is below. So that's going to be an error. So the sensitivity is 5/6. Similarly, specificity is the proportion of negatives that are correctly detected. Negatives, there are 6 negatives in this column, 6 zeros, sorry, 7 negatives, 7 zeros. Of those 7 zeros, 1, 2, 3, 4 are correctly detected by the AI. So the specificity is 4 sevens, which is 57%. And then I can compute 1 minus specificity, and I have this purple point on the curve. So this way, you can actually, for any threshold, you can generate a point in this space. And when you join these points together with a curve like this, that's called an ROC curve. So this green curve is called an ROC curve. By the way, ROC stands for receiver operating characteristic. That's just a terminology from electrical engineering. Don't have to worry about that. It comes from signal processing and so on. And then similarly, I did another calculation for this red threshold, red operating point, and got a point here. Okay. Now, one characteristic of these ROC curves is that they're always sort of increasing like this, meaning that as sensitivity goes up, specificity always goes down. It's a trade-off. Or in other words, as sensitivity goes up, 1 minus specificity also goes up. And the way we eyeball and say that this is a good classifier is to see how high this curve is. Remember, this 45-degree line really corresponds to a random classifier. So you don't want it to be close to the 45-degree line. You want it to be as high as possible. So if you can push this curve higher, that means you've got a better classifier. Higher meaning sort of going towards the top left corner. Okay. Questions? Everyone comfortable with if I give you some data like this as homework? Everyone comfortable with being able to calculate sensitivity, specificity, plotting an ROC curve?
Alpan, one quick question.
Yes, yes.
In order to create, you very clearly explain how to do this, but just for me to understand. So the ROC curve, the curve itself, gets created by first deciding on the operating point, which then determines the performance interpretation of the score into ones and zeros, and then
Yes.
coming out with the remaining metric. That's the precise way you have to create the ROC curve.
Yeah, and for each point on the ROC curve corresponds to a different operating point.
Correct. So that keeps going, if you will, in from 0 to 1 of some sort, I assume.
Yeah. So practically the way you do it in code is to just, if you have a data set with 13 entries, for example, this one is 13 rows, right? You set an operating point corresponding to each row. So first you have an operating point that only picks out the first row as positive and remaining as negative. Next operating point is first two are positive, remaining negative, and so on. So essentially you can only generate 13 points for this data set, and then you join them up.
Understood. But conceptually, you always start with the operating point and then derive the curve.
Correct.
Because the operating point is the way to interpret the result
Yeah.
as either a 1 or 0, and the curve really only cares about ones or zeros.
Yes, but the nice thing about the curve as a whole, taken as a whole now, once you have it, the curve itself, since it encompasses all operating points, we say it's independent of operating point. So it's a nice way to visualize the performance of a classifier without regard to choosing an operating point.
Understood. And later, I'm sure you'll cover how to determine operating point for different types of problems, maybe.
Yes. Maybe I should have more examples, but yes, I do discuss a bit of that. So often what you will see AI ML scientists doing or quoting is, if you ask them how accurate is your model, they will not quote the average accuracy that we discussed earlier in the context of a confusion matrix. Because in order to do that, you actually have to choose an operating point. Right? Because the moment you change the operating point, it will be a different average accuracy. So instead, what they will tell you is the area under this curve. I mean, for those who have some calculus background, it's just the integral under this curve. For those of you who don't worry about it too much. It's just that as you push this curve, you can't, if your model is really good, this curve is going to be really high like that, right? And then the area, if the curve actually goes and touches the boundary, then the area under the curve will be just the area of the square, which is 1. Right? And if the curve is as good as a random classifier, which means a really bad model, then the area is the area of this triangle, which is half. So the area is always a number between half and 1. Half is really bad, 1 is very good. Right? So what they will do is they will quote you the area under this curve, and that's called AUC ROC. AUC is area under curve. Okay, so that's an overall measure of accuracy. It is not practically useful because that's not how you use when you actually use the AI model, you have to decide on an operating point because the model has to give a prediction. Is this positive or is this negative? So you've already chosen an operating point. So this way of quoting a number that is independent of operating point, namely the area under the ROC curve, is somewhat artificial, but it's a good way to track the performance of a classifier in internal AI model development. And it doesn't rely on an operating point. So that's the nice thing about it from internal technical point of view. But when you actually are ready to deploy the model, you have to choose an operating point.
I think that's very important for us to internalize, no? How you interpret this. This is
Yeah.
really for the performance of the model for internal reasons. But
Yes.
when you go out to the world at large, somehow, and you said you'll discuss it later at some point, how you can
Yeah.
determine the operating point, or that's done by the program team, etc. So we have to have an operating point. You cannot. So that's it. It can be a difficult choice, isn't it? What are the characteristics you have to think of? It depends on
So-
what type of problem. Is it diagnostic, screening? Those kinds
Correct,
of
correct,
things.
correct. Those kinds of things. So if it's a health screening problem, then typically you want high sensitivity. So let's just look at this curve. If you want high sensitivity, then maybe let's say you have a restriction that the sensitivity has to be greater than 80%. Now sensitivity here is the y-axis. So you put an 80% horizontal line, and you have to choose an operating point between there and here. Okay? And then you want an operating point, obviously, that is as high specificity as possible with the constraint that more than 80% sensitivity. So you'll probably choose something there. And then as you improve the model, this curve will get pushed up, and basically you then have a choice of doing two things: either increasing specificity at a sensitivity of 80%, or keeping specificity fixed and increasing sensitivity, or just going diagonal. And again, that depends on the characteristics of the ROC curve. I should maybe in the next lecture actually draw some of these different ROC curves and how we would make choices. I haven't really done that.
No worries, Alpan. I think one of the things that comes in my mind, and maybe obviously there are folks who understand this because of their background a little
Yeah.
quicker than others. But this is important, and maybe as additional material over a period of time, reviewed by you, of course, Alpan, folks like Sanchika, Malay, and others, we can start developing additional material, because this is
Yeah,
not
it'll be
intuitive
good
to
to-
everybody. It's not that
it'll be-
easy for people.
No, it's not easy. And it'll be good to actually create some animations where as you improve the model, the
Yeah,
ROC
or
curve
even
goes
some
up
some
and so on.
commentary which says,
Yeah.
which class of problems has high sensitivity,
Yeah.
and then how do you determine that? Some guidelines. After maybe about 3 to 6 months of sitting over this fairly well, I mean applying it, I think people will start understanding this thoroughly. This is not going to come in
Right.
1 or 2 sessions, although people should apply themselves.
Yes. Yes. Okay. So, so in a public health situation, typically we want high sensitivity. I'm going to pose a question to you guys, which is, going back to the spam email classification example that we had discussed earlier. What do you think is the right metric there? Just based on your experiences with handling email and seeing spam come into your inbox, or some important stuff go into your spam folder and so on, what do you think is the right thing to do in terms of optimizing the metric? Let's say you have an ROC curve. Suppose this was the ROC curve for a spam classifier. Where would you choose the operating point, and why? Think about it. What is desirable
So-
from a
so,
spam for a
Alpan-
spam classifier?
Yeah, so Alpan, let me start the thinking process
Yeah,
before we
yeah.
come to the conclusion. At
Yeah,
least.
yeah,
And
exactly.
Malay, you can get in others. The thinking is important. So like you said, if you want a spam classifier, you want it to catch a spam. That's the main thing that you want it to do.
Is that the main thing?
Within the
So this is
main-
an interesting question, right? What is it that you don't want for sure?
You'd never want it to reject good mails. You don't
Right.
want it
So
to ever
yeah,
put
exactly.
a good mail into spam. That is the
Into
most
spam.
important need.
Yeah.
More
Yeah.
than
So assume
catching a
assume I
spam.
call assume I call spam positive and good mail negative. So what is it in terms of positive and negative? How would you frame that?
I want the highest amount of good mails got divided by total mails. I never
No,
want
no,
it
let's
like
not go to ratios. Let's not go to ratios yet. Let's just say you don't want good mails ending up in spam,
that. Correct.
right? So you don't want negatives to be classified as positive, right?
Correct.
So you don't want false negatives.
Correct.
What about false positives?
You can tolerate some.
Yeah, if spam comes in your inbox, fine. I mean, it's just an irritant, but it's not going to destroy your life. Whereas, a good mail going into spam can actually destroy your career. It's an important interview call or something, right? Anybody else who wants to weigh in on this?
I think it will take some time for all of us
Yeah.
to just get used to one
Yeah.
terminology. I think we
Yeah.
must first think
So-
of what is the domain and then translate it to this false positive, false negative, true positive, true negative thing. A little
Correct,
better.
correct. So yeah, so first you decide on based on the application problem and what you're calling positive or negative. So in this, I guess it's clear to everybody that you can tolerate false positives. Again, reiterating, false positives are good mails being classified as good, meaning negative mails being classified as positive, which is spam. Um, uh, Sorry, false positives are. Have I gotten mixed up? False positives are actually, yeah, you don't want false positives. Sorry. You don't want good mails being classified as spam. So it's classified as positive.
So precision would be important, right?
So precision would be important. You want your false positives to be low. So when you call something spam, it better be spam.
Right.
Yeah. The other way to also frame it, it again depends on the prevalence, is you want your specificity. Let's see. So you want your specificity to be high, right? You want all your negative emails, meaning non-spam emails, to be detected correctly, not to be detected as spam. So you want your specificity to be high.
So Alpan, would it be correct
Yeah.
to say if you would want your specificity to be high, but
Yeah.
it's okay if the sensitivity is not as high?
Yeah. So sensitivity is the proportion of spams that actually, proportion of actual spam emails that go into your spam folder.
Right.
It's okay if that's not high. Even if you like only half of the spam emails go in your spam folder, the remaining half are in your inbox. It's okay. It's an irritant, but it's not life damaging.
So in this case, you would choose something like operating point 1, right? Because
So you would choose something like an operating point 1, exactly. Something where the specificity is high, but you don't care much about sensitivity.
thank you.
Or something even below 1, ideally. So somewhere here, right, where you have even higher specificity, maybe lower sensitivity. Now, as I've said, so this is basically the way to think about these types of problems. And as I've said earlier, one of the characteristics of specificity and sensitivity, and therefore of the ROC curve as well, is that these metrics don't depend on what? Can anyone remind me?
Prevalence.
Prevalence. right? If you change the prevalence of ones and zeros in this, it's not going to affect sensitivity and specificity. It's not going to affect this curve. This is also another reason why people often use the ROC curve. But there are other metrics that do depend on prevalence, and they are the precision and the precision, false discovery rate, accuracy, and so on. So there's another curve that's often used, which is called the PR curve, or the precision recall curve. Now, this is a curve where you have precision on the y-axis and sensitivity or recall on the x-axis. Now, the nice thing about precision is it tells you, well, of the number of examples that were predicted to be positive by your classifier, how many were actually positive. So it's a very practical metric in many contexts, because when you actually use your classifier, it's important to know this. Right? Every time my classifier makes a positive prediction, see how many times is it actually right? Whereas what sensitivity tells you is, of all the positives that are out there, how many will be recovered by my classifier? How many will be correctly detected? It's a somewhat more abstract notion. Whereas precision, you can readily measure without even knowing how many positives are out there. Yes.
So Alpan, how would the F1 score, plotting an F1 score would
Don't worry about F1 score right now. Yeah. F1 score complicates things. Don't worry about F1 score.
Oh, okay.
Right now, let's just, restrict to precision and recall. F1 score is, it's good for, again, it's good for internal model development sometimes. But it's often, well, I would say most of the times it's not really useful in practical situations.
Okay. So the value that F1 score gives is not exactly the same that as the PR curve gives.
No. F1 score is again a metric that's computed based on a threshold.
Oh, okay.
Okay. So yeah. So where were we? I just have 1 minute left. I'll just go through this and then leave you to think about things here. I think it's the same. It's the same table, the same 3 operating points, and now I'm computing precision and recall. Right? So again, let's just go through a calculation. If you choose this first operating point, that means that you are predicting everything above it to be 1. That's the predicted label. Everything below it predicted to be 0. So the thing about precision, it only cares about what's above it, because those are the ones that are predicted to be 1. So all 3 of these patients are predicted to have label 1, but only 2 of those labels are correct. So the precision is 2 out of 3, 67%. Right? And we've already calculated recall earlier. Recall is the same as sensitivity. Here, everything above is predicted to be 1. So there are 8 predictions, 1 out of which only 5 are actually 1. So the precision is 5/8, and so on. Right? So now you can generate a similar curve, which is the precision recall curve. The nice thing about this precision recall curve is it's very practically useful. So there's two observations. One is it immediately tells you that if I'm using my model, say it's integrated into an app, and I start using it, and I do predictions on 10 patients, let's say, and out of those 10 patients, I predicted that 7 are positive. Out of those 7, I can immediately check how many of them are actually positive. Right? And say 6 are actually positive, I know what my precision is. For this, I don't need to know what is the total number of positive patients out there. Whereas for sensitivity, you do need to know that. So this is very practical in that context. The other thing is the baseline value for prevalence, for precision, is in fact the prevalence in the population. So if you had and the reason that is the case is because if you had a random classifier, then the precision of a random classifier would be the prevalence. So just imagine you have the model that's integrated into your app is all it knows is that 1% or say 10% of your population is positive. So every 100 times, 10 times it predicts 1 just randomly, and 90 times it predicts 0. The precision of that classifier would be the actual prevalence in the population. It would just be 10%, because it always has a 10% chance of getting it right. Okay. So typically when we plot a precision recall curve, it's good to always have a comparison to the prevalence in the population. That's your baseline for precision recall. Okay. I think maybe we should stop here for today. Can take a couple of questions. Okay, no questions. We're done. Thank you.
Thanks, Alpan. Thank you.
Thank you.
Thank you.